So howdy everybody, my name is Pete and today we're here to talk about The Genesis Machine by Amy Webb and Andrew Hessel, a book about bioengineering. So Amy Webb is a quantitative futurist and the founder of the Future Today Institute. She writes about science and technology for publications such as the New York Times, Wired, Fortune, and Mother Jones. Forbes named Webb one of the 5 women changing the world, and she was honored as one of the BBC's 100 Women of 2020. Andrew is a microbiologist and a geneticist who has worked on the leading edge of genomics, bioinformatics, and synthetic biology. He is the co-founder of Humane Genomics, Inc. and Genome Project Right. Amy, Andrew, welcome.
Thank you so much for having us.
Yes, thank you.
So I'd like to start by asking, so in high-level terms, what is your book about?
Sure. So first of all, thank you so much for having us at Google Talks. We really appreciate this opportunity to talk to you about an area of technology that we think is exceedingly important. It's actually one that, as an organization, you're involved in, and that technology is biology. This is a book about the technology that's going to allow us to edit, to redesign, and to ultimately create new forms of life. It's going to give us options to deal with existential threats like climate change and novel pathogens. And it's also going to help us improve human longevity. So the technology that we've described in this book is called synthetic biology. Now, for those of you who work anywhere near artificial intelligence, which is a lot of you, synthetic biology is similar in that it's an umbrella term, just like AI is an umbrella term, to describe other technologies. This is an emerging area of science that involves redesigning organisms for useful purposes by engineering them to have new abilities. And this field combines engineering and design, computer science with biology. And what researchers are trying to do is to get down to a molecular level in order to make organisms adapt, to influence how they change and evolve, and basically give them different types of abilities. And this stretches across all different industries. Obviously, life sciences, health and medicine is one, but new materials, and as we're probably going to talk about at some point today, it also influences what the future of computers can do and look like. All of these techniques make it easier to engineer biology. And one of the things we think is true is that 10 years from now, or perhaps even before then, people will be talking about synthetic biology the way that we currently talk about artificial intelligence, which is to say, there's a whole lot of people who are aware, generally speaking, of what that term means, and that it's permeated enough of our business, our research, our everyday lives, that it's sort of risen to a general level of consciousness in society. The reason that this is so important right now, given that synthetic biology, just like artificial intelligence, is on a very long developmental track, a long time horizon. But the reason that it's important right now is because of a couple of key things. First of all, because of SARS-CoV-2, this is the virus that causes COVID-19, it acted as a catalyst for sequencing, for synthesis. It actually asked us to change our mental models for pathogen detection and how we inoculate people. And that has attracted an enormous amount of investment. So a lot of this work was already underway, but there were finally some use cases in the marketplace. And we'll probably talk at some point about what some of those investments look like. But suffice it to say, there's just a flood of capital right now being directed at SynBio, which probably means that we'll start to see some accelerations. And that's good. However, some of the developmental track that we're seeing in synthetic biology potentially mirrors some of what we've seen in AI, which is to say, we don't want to see a synthetic biology winter the way that we did with AI, and we want to make sure that people have expectations that mirror plausible reality. The other two reasons have to do with geopolitics. So technology is evolving much faster than any regulatory agency's ability to really think it through, which means that we've got some competitive goals between countries that may not be aligned. So that's the second reason, and we're seeing a little bit more of that, especially in recent months. Lastly, we have some serious crises that we're going to have to manage in some way. So obviously, we've got a climate emergency that we're trying to manage, global food insecurity, a shortage of water. Synthetic biology gives us options that we did not have in the past. There are risks associated, several of them, and those range from genetic privacy and genetic surveillance to managing what we think is very likely going to be a misinformation crisis that dwarfs what we're currently contending with. But the promise of synthetic biology, and indeed the promise of the book, is that if we can develop our thinking on all of this technology today, and if we can meet each other in the middle to have difficult conversations about what the futures of life looks like, and that's going to include things like intellectual property, then we're going to be closer to some solutions for those existential challenges that we're facing. The book is a book about science, but it is not really a science book. This is a business book. This is a tech book. It's a policy book. And mostly it's a book about people. The book opens with some very detailed, intimate stories from Andrew and myself. And as we go through, we introduce different scientists, researchers, everyday people, and really show in vivid detail how this field of synthetic biology is starting to flourish. And ultimately, this is a book about you. The reason that we wrote this is because we want you to be thinking about yourself in the future, your life. And we want you to start working through the decisions that you are at some point going to have to make within your own lifetime about how you will use and benefit from some of the products of synthetic biology. Because the decisions that ultimately you make, they're going to have benefits, but they could also have consequences.
Awesome. Thanks, Amy. I'm going to point out that in the YouTube chat, you can go ahead and leave some questions, and later there'll be some time for Q&A, but I'm going to start off by asking a few pre-prepared questions for our authors. So my first question is, you mentioned COVID. Can we engineer our way out of this pandemic?
I think we have been re-engineering our way out of this pandemic. I think we've all been educated significantly in the last couple of years on a variety of topics: virology, epidemiology, immunity, and so on. It's common knowledge now that the vaccines that were prepared for COVID were done in record time, 9 months. I think the closest comparator was 4 years. So that's pretty significant. And that's largely based on the tools that have been developed, the tool set that's emerged for synthetic biology. It's one of the first programmable vaccines. The manufacturing of that vaccine was done in cell-free systems, a significant change from the older ways of producing vaccines that often relied on growing viruses in eggs. Diagnostic tools also benefiting from synthetic biology in that we were able to rapidly make new forms of diagnostics, both nucleic acid-based and protein-based, like antibodies. And moving forward, I think we're just going to get more experience using these tools, one, to respond faster to emerging outbreaks, to detect them sooner. And really, I think this could be the largest advancement in public health that we've seen in 50 years.
I'd like to add just a little bit of additional dimension to that. So I'm a professor of strategic foresight at NYU Stern in the MBA program. And part of what I teach students how to do is to model plausible next order outcomes. What's really interesting about COVID and our response, the messenger RNA response to it, is that this is technology that actually had existed prior. We just didn't have use cases, not just to figure out how to get that to market, but also how to shift a little bit the regulatory processes. And suddenly now people are aware of what this is. We have some regulatory approvals in place, which means that there are additional avenues and opportunities now to really exploit this technology, which is why you're hearing about universal flu vaccines and new, I put in quotation marks, air quotes, therapeutics for cancer, since to some degree, the research that was being done in this case was related to cancer before it was being applied to COVID. So as Andrew mentioned, like there is just a ton of really interesting research now being done and products that we're going to start to see in the marketplace at some point.
So can genetic engineering help with climate change?
Oh, there's so many areas that can help with climate change. Part of the reason why we have the climate change issues that we have today is just humans have been so incredibly successful over the last 2 centuries, but we've been relying on essentially banked carbon to power civilization. The really wonderful thing about synthetic biology is you start to be able to control carbon cycles in completely new ways. So we can start making fuels that are neutral. We can also start to repair damage that's been done in the environment by shifting away from chemical production to biochemical production of things like plastics, which we use every day. And really just starting to move whole sectors of the economy like transportation away from carbon-based systems to electrical and biochemical based systems at every point of manufacture. So there's so many different ways, food production included, because a big source of climate change is really just agriculture. Amy, I'm sure you have a lot to add to this.
Yeah, well, I can pick up on the agriculture thread. So as we are talking to you now, just a couple of weeks ago was the Super Bowl. And in the United States, Americans ate 1.45 billion with a B chicken wings. That is an extraordinary amount of chicken that everybody consumed all on one day. And 1.45 billion chicken wings requires like more than 700 million chickens. And actually even more than that, because on traditional commercial farms, there's a lot of chickens that don't make it through the process. Now, what does it take to get that many wings? You need commercial farms, you need antibiotics, you need hormones, you need specialized feed. You need to create a system that will produce that scale in a relatively short amount of time, which, let's be honest, is not good for the environment. It doesn't really help out our sustainability goals. It's probably not great to consume huge quantities of that type of chicken. It's also not great for the chickens. So what if there was an alternative way to produce that same type of meat that didn't, cause some of the same challenges? And there is a way to do that. It's by taking cells, stem cells from chicken, and putting them into what looks like an enormous pressure cooker. It's called a bioreactor, and feeding those cells. And let's say that they're cells from heritage chickens versus the commercial chickens that we have today. So healthy, beautiful, old, chicken lines. And we put those in a bioreactor with amino acids, create the warmth and the comfort that would have been present in a mother hen. Over a shorter period of time, those cells divide, they multiply, and you wind up with chicken meat. Now, that meat has already gone on sale in Singapore, which tells us that it's already passed through, it took 2 years, a regulatory process. There was consumer demand, and it scaled, in a small way, but it scaled. The portion size is around $17 for one serving right now, which is a far cry from a 10-cent chicken wing. But this is early stages. Now, this has profound implications on the cold chain. So where chicken gets created and moved around, Singapore, which eats an insane amount of chicken every year, would be able potentially to produce all the chicken that it needs without having to rely on importing from other countries. Or the United States could have a bioreactor in every city and generate all of the, let's say, chicken that it needed ahead of that next Super Bowl. So, that's all on the near-term horizon, but why stop at chicken? What if the freshest sushi that you've ever had in your life, was maybe made in like a bioreactor in Oakland, and you never had to farm off the waters of Japan and flash freeze and fly fish, fresh fish all around the world. So this totally changes our mental models about where our food comes from, how that agriculture, aquaculture process impacts the local environment, and it drastically shrinks our supply chains. So this is, it's not going to be happening overnight, but this is the path that we could be on in the relative near term, which potentially solves part of our food crisis. It addresses some of our climate, challenges, reorients the cold chain and the global supply chains, and actually potentially creates areas of new economic activity in different parts of the world.
That sounds like some really wonderful news. So what do you think are the biggest benefits to humankind you see that genetic engineering could bring us?
I'm going to start with just reiterating food is the first medicine. It's something we need on a daily basis. And that is one area that if we're going to keep growing population and reducing the effects of industrial agriculture on our planet, is going to be a massive driver. In fact, last year, about $18 billion was invested in synbio startups. About 10 billion of that went towards food. The second biggest area is medicines. This is such a revolutionary technology for making medicines, because medicines become programmable. We can start to moving away from chemical synthesis. We can now do biochemical synthesis of many drugs. They're bioactive. They can be produced in small batches or at scale. They can be even individualized to single people, which is completely new. It's really a reshaping of the biotech industry along the same lines of what we've seen in the movie industry. Really going from just big blockbusters to YouTube, and just digital studios in general. So that's a massive one. And the third one I'll just point out that is really significant is we live in an engineered world. So we build the world around us. We use a lot of natural materials today to build our environments. If we can start using synthetic biology to make those materials, and already there's groups that are using synbio or cellular systems to make bricks and cement, woods, without having to grow the tree, and so on. I think there already synthetic leathers are making it through the automotive industry and furniture industries. We can really start to use materials that are sustainable, can be manufactured in small batches or at scale, for really improving humanity and the way we live, how we treat health, and ultimately protect the planet.
Yeah, there are a couple of the examples that we give in the book related to materials science are nylon. We use an extraordinary amount of nylon, which is already synthetically produced, but there are new techniques to be able to create durable materials, again, without relying on some of the practices that are currently unsustainable for a variety of reasons. There's also a geopolitical aspect to some of this. The places where we source some of our raw materials are fraught and very tied up with current geopolitical challenges. So this gives us the ability to unhook ourselves from some of the more tenuous supply chains and to sort of create other opportunities to get some of the same materials. On the human side of things, again, this is a little bit further out, but we're very likely looking at a future where we can influence our offspring. And this is not about creating designer babies. It's about creating healthier offspring and just making it easier for people to create their families. We have a ton of examples in the book, but just a few include things like genetic surgery, where we can make genetic edits to embryos to correct major errors that might otherwise prevent them from being born, and in the process create many more embryos than we do today to optimize selection. Pretty soon, at some point, we'll be able to make eggs on demand. So there's an emerging technology called in vitro gametogenesis, IVG, which would allow same-sex couples to create a baby using their own genetic material without having to seek out donor eggs or sperm. And there is additional technology that would shift really how we think about parenthood from the current two-parent construct to a one-parent construct, or a multi-parent construct. And I know that these are challenging ideas to think about, but this is not being done in the name of weird, freaky science. This is really about helping to solve some health issues that exist today and trying to improve the quality of life and life itself. And one might argue that if we've got this technology available to us, don't we have a moral obligation to make sure that we're doing everything we can to create healthy offspring?
Fascinating. So in the book, there's a ton of ideas for new things, like a battlefield lab where you could build countermeasures to biological attacks as they were being deployed. What are some of your favorite ideas? Which ideas, in your mind, hold the potential to help humanity the most?
I'm going to say so I look at this technology as essentially opening a gateway to programming life. And one of the technologies that I just want to continue to see be developed is essentially the cloud laboratory. Cloud computing, of course, is taken for granted today, incredibly powerful. But labs are a real bottleneck for access, and we don't all have the ability to go and create a lab in our homes. So the cloud lab, essentially the fusion of biological technologies and robotics accessible through a web interface, is really powerful. I started working with some of the early groups doing this about a decade ago, and was just amazed, because instead of spending millions of dollars to outfit and equip a laboratory, you could really start doing some engineering work almost immediately. So I think that the cloud laboratory will open up the ability to do synthetic biology to a much broader audience. I think the digital technologies that it's founded on will help put guardrails in place, help community as we grow in the same way that we see in the software developer community, for example, to be able to share information and learn, and ultimately start producing outputs in a controlled environment where it's very easy to ensure safety, and that biosafety protocols are being fulfilled, and to share ideas and results. So I think that's a big one for me. Amy?
Yeah, I think for me, it has to do with, I guess, two things. One, how we advance computing architecture, which I know is being worked on in different ways, but at some point, you can only condense so much compute into so much space, and it's sort of the model breaks. So as you're thinking through how, transformers work and the evolution of deep neural nets, and how that entire ecosystem starts to evolve, I think it's really interesting to start thinking through how might that evolve, not just figuratively as it relates to biology, like modeling, some of these neural nets on how our brains work, but literally. And there are some startups and some researchers kind of exploring this space right now. There's a company called Roswell Biotechnologies, and last week or 2 weeks ago, maybe, they unveiled some research that had been bubbling up for a while that they've been working on, and it's a molecular microchip. So this is a semiconductor chip that's smaller than a fingernail, and it can grab an individual molecule and it can read it. We've got microchips in basically every device. And again, microchips are another area that are intertwined with geopolitics. And it just gives us, if we're able to start thinking about computing architecture very differently, it just gives us additional ways to think through, computing. This particular chip has 16,000 sensors, and each one can latch onto a molecule, like a protein from a virus or an enzyme that can decode DNA. And then it can start to sort of read that molecule using different changes in electrical currents. So what I get very excited about is there a future in which sort of living computers, living machines become a practical reality? And if so, how does that really start to shape our experience? This is kind of the inverse of the nanobot crisis scenario that I know we've all heard 1,000 times before. This just treats computable interfaces in a very different way. And again, if we think of binary versus ACTG, we're still dealing with code. So can we start thinking about code in a different way? The other thing I get really excited about is agriculture. Agriculture really has not evolved fundamentally in more than 10,000 years. If we have the ability to re-engineer plants, I grew up on what I like to consider to be the south side of Chicago, some bordering Indiana. If any of you out there know what I'm talking about, you kind of get the joke. There's a lot of corn east of where I grew up. And corn takes up an extraordinary amount of space. It takes a lot of effort and resources. And basically on one stalk, you get 3 or 4 ears of corn. It'd be really interesting to think about having 10 or 20 ears of corn on a single stalk, making the stalks taller, and also putting them indoors. And if, again, I know this all sounds a little sci-fi, but it's plausible that if we can't control the conditions outside, we could at least start to control the conditions inside and really reshape our relationship to how we grow the food that we need to eat. And what's really cool is that Microsoft is actually working on this very problem right now, and there are parts of Google that are working on this problem too. It's just in both of your companies, you're not entirely aware of all the research that's happening. And, I could see a future in which, Alphabet and Microsoft, in addition to providing the computing systems that we use, also help provide the agricultural, the sort of agri-tech platforms that we use, which means that in the future that starts to reshape jobs and it starts to reshape different industries, which I think is really exciting.
So to what extent can aging effects be reversed? I'm starting to get older now, and I'm wondering, are these innovations going to be in time for me to live a lot longer?
We have gotten that question from every single person that we've talked to. So Andrew, would you like to do your thing?
Yeah. So can aging be reversed? I can say that the R&D there is looking really positive. We're learning more and more because we've essentially taken dissection down to the molecular level now. We're starting to get insights into the biological aging process from research in model organisms, and again, just even the variation in aging in human populations. So we're starting to get a better understanding of some of the modulators in aging. Reversal is actually a key part, Pete, because unfortunately, if you're trying to do a clinical trial where the outcome is determined at the end of life, is really difficult to set up. But you can run clinical trials where you're taking someone or a model organism that is already aged and rewinding, essentially using a genetic or other therapy to essentially restore function. And those some of the results, some of the R&D that's happening in that space is really exciting. Looking a little broader, there's some fascinating experiments that have been done where just reprogramming cell death has produced dramatic results. Instead of having the organism age and accumulate a lot of what we call senescent cells, which are cells that are still alive, they're still metabolizing, but they're no longer growing and dividing. They're almost zombie cells. By doing a few genetic tweaks to those, we can have those cells, when they reach that senescent state, self-destruct. And in model organisms, when that program has been loaded into the creature, it dramatically changes the aging process, because as the individual cells get old, they die off and are replaced by a healthy cell. So we've seen trying to get that treatment into people will take a while, because it essentially involves doing embryo engineering so that all the cells have that program. But just understanding what's happening in that process opens the door to therapeutics that could keep us living a lot longer, a lot healthier. Will it happen in your lifetime? Well, it can, but we'll have to do a little bit of acceleration on the regulatory processes today that are really conservative. And as people know, it can take 10 years or longer to develop a new drug and bring it to market. That doesn't bode well if you want to get a few innovation cycles in on these technologies for longevity.
We actually cover senescent cells in one of the scenarios in the middle of the book. So for those of you unfamiliar, a scenario is a time-tested tool that is used in strategic foresight. It's a way of using data and evidence to model out plausible next-order impacts. And sometimes those scenarios are strategic. Sometimes they read a little bit more like speculative fiction. So in our book, what we've done is create 5 scenarios that are speculative fiction, all rooted in data and evidence and research, but try to understand how things might evolve. So the aging question we explored and talked, sort of helped you think through this phenomenon of zombie cells and what initial therapeutics we might start to see. But we also ask you to contemplate what the next order impacts might be of lots of people living much longer, very healthy lives, and how that might challenge some of the structures that we have, whether that's Supreme Court justices living and serving for 80 years on the bench. There's a part in the book where not Tom Cruise, Ted Cruz. What is wrong with me? Ted Cruz? Senator Cruz. Ted Cruz, yeah?
Ted Cruz. Yeah.
It's weird that I said Tom, though, right? I don't know what that means. Where Ted Cruz is like, he's still senator, well into his 120s. And there's my hometown Chicago Cubs they get the World Series 2016 team back together and refuse to retire. So I think what we're trying to say here is there's always opportunity on the horizon, but with that opportunity, there are typically costs associated. And while we want to pursue treating age as more of a pathology where everybody lives extraordinarily healthy lives right up until the very, very end, and then we exit in as fast and painless a way as possible, we have to think through the repercussions on society and what that means for the workforce, for people attaining leadership positions in their organizations and things like that.
So my next question, I've just always wondered, could I do some kind of genetic engineering to do a gender or sex swap by DNA editing on a grown human?
Oh, that's a tricky one.
That's a thorny question.
That is.
Andrew, you get to answer that one.
The short answer on that one is right now we don't have the technology to do that. And that's because we don't have the technology yet to change the genome in every single one of our 50 trillion or so cells. There are some interesting ideas on how we might do that in the future. And some of those have been explored in science fiction books that have come out in the last few years, kind of looking at things like CRISPR technologies, which is a gene editing technology, and something called a gene drive, which is essentially a genetic change that can propagate through the environment or through an organism. But that being said, if you can change your sex, you could also essentially add new functions to every single cell in your body and not do it at conception, which is really fascinating. So you can definitely bet that people are going to be working on this type of technology. And once we have the chassis that allows us to do global upgrades in an organism, if it can be achieved, we're going to be trying a lot of interesting things, including sex changes.
So that may answer the next couple of questions. Oh, Amy, you were going to say something.
Oh, I was just going to say, one way, if this is kind of new to you and you're scratching your head a little bit and trying to remember what you studied in high school biology, one way I think I find to frame all of this is within the realm of permissions. So what we're talking about effectively is having super admin permissions to life. which is to say, it's you can observe permissions, you can change them, you can control them. So it's kind of like right level admin access at the root to life's source code. And that really, I think that might help you wrap your head a little bit around what it is that we're talking about and why it's so profound. We're doing this on tiny little micro programs at the moment, but having root level, super admin access is going to unlock incredible capabilities. And just it might be an easier way for you to think about all of this.
We're certainly getting that root level access to cells.
Yeah.
And we have already synthesized the first cellular genomes.
Yeah.
That was done in 2010. And we're getting better at writing the complete genome of cells. That being said, when you're dealing with a multicellular organism, you've got two problems. One, how do you go and rewrite that cellular genome that might be there already? And two, how do you do it for every single cell when every cell is actually let's just say every cell is firewalled by both internal and external systems.
There's actually a pretty cool consortia, if you're interested in this, now that we're on a weird tangent, called the Human Cell Atlas. And there's many hundreds of scientists all around the world working on trying to create literally an atlas for every cell that exists. It's a Herculean and probably somewhat Sisyphean effort, but it's pretty cool. And once we have these maps and greater understanding, then we can start going in and tweaking. The opposite side, not the opposite, but another approach to this is what Andrew just mentioned. This is trying to build out sort of a minimum viable genome and booting that up. And as he mentioned, within the past decade, we've had the first, or even 12 years now, the very first life form that technically had parents as computers got booted up, which is incredible, really incredible to think about.
I think that may answer my next couple questions, like could I grow an extra arm, or could we give ourselves gills so we could breathe underwater? It seems like it'd be the same answer for the same reasons. So let's jump on to the next question after that, which is, what does this mean for sports? I mean, I've always heard how steroids were bad, but I mean, if you could genetically engineer someone to have much bigger muscles, does it become a matter of who can engineer the best build?
I think we're already bumping up to that. So even before we start engineering ourselves, we're just the technology of IVG that Amy mentioned, which could potentially allow a fertility clinic to produce thousands or hundreds of thousands of embryos at once, allowing the parents to screen for the best of those embryos. Really changes the game, just because we kind of accelerate our own evolution. We start to put our choices, our selective choices, on top of just natural kids. When we start actually editing or designing and building those genomes, and I see one of my kids running in the background now.
Speaking of genomes.
Yeah. then all bets are off, and we might very well have to start an X-Olympics that just allows us to compete, with all the guardrails off. I'm not sure what that looks like.
We do explore in the book, and this is one of the risks, right? What if the current digital divide that we're experiencing in the future is more of a genetic divide, and we have modified humans, and those humans who, for whatever reason, didn't believe in, couldn't afford to be modified? Then how does that start to bifurcate and splinter society in different ways? But as this relates to sports, honestly, it doesn't matter what science does. People are always going to figure out a way anyways to cheat. I mean, somewhat recently, Zwift, which is the indoor cycling / gaming platform, somebody robo-doped at a cycling tournament. Basically, you have to ride a whole lot, and then the greater your output is and the more time you spent, you level up and get better and better bikes, and the better bike that you have, the more points that you can attain. It's kind of like a mishmash between a Peloton and like an e-sports system. Anyways, this kid bought an algo that continuously ran, which meant he had the highest level bike. You still have to be in shape, but he shows up at this tournament in the UK and just blitzed everybody. And there was money at stake. So my point is, like, regardless of what athletic activity or sports activity, whatever it is that we're doing, and regardless of what science or technology exists at that moment, somebody's going to figure out an exploit. That has always been the case. It will always be the case. So should we worry about synthetic biology because it potentially provides an advantage to some over the others? I don't know. Honestly, of all the things we could be worrying about, that's probably not at the top of my list. There are plenty of other ways to game the system in the interim, as we saw at the Olympics. Again.
So moving on from changing humans, the next few questions I have are about changing animals. So I've always wondered, could we make better pets, or maybe Pokemon, or maybe fire lizards like Anne McCaffrey's book Dragon Song?
Let's just say that the engineering of pets doesn't have the same ethical constraints as engineering humans. And as this technology develops, I think we will see plenty of experimentation there. I hope it's done ethically. We've already got the first genetically engineered pets, which were glowfish. We've, of course, all the dog breeds out in the world were human directed over thousands of years. I think as we start to explore the capabilities of some of these technologies, I think we'll see it play out in the pet world, primarily with dogs and cats, which are the pets that we generally keep. It's already happening in the world of animals. We've cloned. It's starting out with cloning, and there's been 25 or 26 large animals cloned now for a variety of reasons. But the next step after cloning will be the editing of those genomes as well. So I expect that we may see gene-edited racehorses before we see a lot of gene-edited humans, but eventually it will come down into the pet world as well. Now, as for dragons, I love the idea, and we.
Get on it, Andrew. Make us some dragons.
Well, I'd love to. I'd also love to create banshees like we saw in Avatar, because that looked like incredible fun. And actually, I was doing some research. There was, in prehistoric times, there was a creature that had the wingspan of a Cessna. And that's the type of organism engineering I would personally love to see us get better at moving forward, because as much as it might be fun to ride in a drone aircraft to work, I'd really like to ride my Banshee.
That may be, so the two areas that are actually in progress. One is sort of rewilding and de-extincting. So in an effort to, again, like learn more about our genomes and all of life, there's a body of work. Lots of researchers are, taking DNA that's been preserved for animals that are now extinct and trying to study their genomes and learn more about them. And some of those efforts are leading to what's called de-extinction. So George Church, who Andrew and I both know, has a project to de-extinct a woolly mammoth. This is not for the purpose of like opening up a restaurant and selling woolly mammoth burgers or having a woolly mammoth zoo. This is about a really novel and interesting approach to dealing with climate change, believe it or not. At some point, way up in the north, enormous animals stomped down the permafrost layers, and they were part of the ecosystem that ensured that enough snow melted, enough of it stayed frozen, it kept the permafrost layer compacted, things like that. So there is some work there. Now, does that mean that someday you too might have an ibex or a tiny little miniature woolly mammoth as a pet? I don't know, maybe. But I don't think that's the explicit purpose of the research. Now, on the other side of things, in livestock cultivation, so China, which had a huge part of its swine population wiped out due to African swine flu and just some inhumane practices in China, they engineered super pigs. So these are pigs that grow faster, that have thicker tissue, They can withstand heat and cold more easily. And they're specifically bred and engineered for food, but they're also bred and engineered to withstand, some more environmental conditions and to try to grow faster. So again, I don't know that you want a quadruple muscled, super pig as a pet. George Clooney at some point, I think, had one of those little pot-belly pigs. So, never say never, but that's what's, currently happening.
Okay, one last question, then we'll go to some questions from the audience in the chat. So in your book, you recognize that there are 9 risks of genetic engineering, and some of these risks could affect our future. So you've identified a lot of important things that need to be done for humanity's safety, but I don't really see anybody doing these things. How do we get them to happen, and how can we, your listeners, do something about them?
Yeah, so this is a pretty easy question to answer. So there are serious risks. Biology tends to self-sustain and to propagate. And at the moment, we don't have, beyond what's called germline editing. So this is when you make an edit, for example, to an embryo, and it's heritable. So whatever that is passes down from generation to generation. There's fairly widespread agreement on not doing germline editing in humans. But outside of that, every country really does have a different approach. In the U.S., we regulate the final product versus the process. Europe has different countries in Europe have other approaches. China's doing its own thing, and so we're going to have to figure out a way to get alignment on not just what those processes and products are, but also the approach to genetic surveillance. And who owns, the questions that we have today, and this is my big concern about the future, the questions that you all are hearing a lot about: who owns your data? Can data be owned? Who owns your face? Who owns your biometrics? And should the big tech companies get broken up? I think it would be catastrophically bad if we wind up having those same conversations within the realm of biology. Who owns your genetic data? What does genetic surveillance look like? How can I guarantee my genetic privacy? And should we break up big biotech? I mean, I think that we can avoid that now. The way to do this is to incent organizations to come to the table through shared processes. Basically, the model that we suggest in the last part of the book is all recommendations on how to move this forward. The model that we use is based on Bretton Woods, which was created in the aftermath of World War II to help mitigate and manage the global economy in a way where everybody could benefit. We think there's a similar approach that could be used for genetic data and processes and products and all the rest of it, where signatories would come together, they all benefit, and there's a little bit of game theory thrown in. So if somebody starts to go astray, then they get punished. So we think that there are some solutions, but again, this is going to require a different mental model. We have the additional challenge in the United States of having, we don't have alignment on when life begins, and therefore what we can and cannot do with embryos and stem cells. That's going to be a challenge for us going forward, because if we can't come to terms and align, then that's going to make it difficult for us as a country in the United States to have these conversations with other countries. So we think that there's a possibility. We also want individuals and people to do this work also, but we think that the approach there would be licensing. Like, you have to get a driver's license to drive a car, and get a license to operate biology. Again, we think that there are some creative opportunities here, and it's just a matter of getting them started.
I'm just going to say, I think one of the things that we've all learned in the last couple of years is that our epidemic and pandemic preparedness needs a serious upgrade. I think that's one of those things where we can agree to work together. And it looks like better public health at the other end of the pipeline. And this has been a great refresher course on how to deal with a pandemic, and I think we'll improve moving forward. The other thing that I'll just leave with you, Pete, was something that I wish that I had when the last time I did a Google talk, and that was Google has done an incredible job opening up the world with Google Earth and just creating an infrastructure to layer on more and more data onto a ball that goes through space. I would love to see essentially the equivalent version for a cell, where it could become very real for people, where they can move through a single cell and understand the relationships and dynamics that are happening inside a single cell. I think that would be an incredible platform, and one that's overdue. And there's groups working towards that now with whole cell modeling, but they are, let's just say, they're underinvested in and just don't have the compute capabilities at this point. But I'd love to see that happen. I think it would be a great entry point for the world.
Okay, awesome. Let's move to our questions from our viewers. So we'll display them across the bottom. I'll read them for you. So what thoughts do you have on stem cells, and if new parents should get umbilical cord blood stem cell for future therapy?
Oh, happy to do that. Stem cell, well, cord blood banking was really big 25, 30 years ago when we couldn't generate stem cells in the lab. Today, we have the ability to generate stem cells pretty much on demand, which is great. So a lot of people banked cord blood as essentially a biological life insurance policy. It developed some great biobanking techniques. Very few withdrawals from those biobanks to actually treat any children with those diseases. So if you can afford it, it's not going to hurt to bank those cells. Today, the technologies for generating stem cells continue to improve, and the treatments that follow from that will continue to advance as well.
Did you guys bank your cells? I don't think I've ever asked you that.
We did not even, we were never presented with the option to bank cells, but now I actually want to bank my entire family's cells, because you don't need stem cells to do that today. You can generate them on demand. Yeah. But I really believe everyone should have, if they're thinking about their biological security, should be sequenced and bank some nuclei at some point.
So I guess we're all best friends now. So I'll just tell you. So this is a huge argument my husband and I had. I was like, take the cells, bank the cells. While you're at it, let's chip our kid. Like, I had a whole technology suite planned, and got overrided on everything. But Brian, he was concerned about two things that he reminds me of all the time. One is, how do we ensure in perpetuity that the stem cells are viable? And, how do you change custody? Our mortgage keeps getting bought by company after company. Like, what happens if the same thing happens to stem cells as they change custody over and over again? And, do you at some point lose custody? Is there a third party? So he had like a billion questions, and I didn't have answers to them. And the second thing had to do with privacy. He's like, what person has, all I do is talk about genetic surveillance and privacy and who owns our data. And yet I have both a Google device and an Alexa device in my home. So he loves to remind me of the enormous hypocrisy of it all. Anyways, I didn't bank our cells. Yes, oh well. I wish I had, but I haven't.
It's not too late, Amy.
It's not too late. It's not too late. Maybe you can have that conversation with Brian and me at some point.
I'd love to. In fact, I've been having that conversation with a lot of people these days.
Good.
Yeah.
Okay, let's move on to the next question. So from Ivan Smirnov, how does synthetic biology flourish in a society where GMO-free is such a successful marketing slogan?
Thank you. I love that. I love what you said there, that GMO-free is a successful marketing slogan, because that is exactly what it is. At some point, to be fair, there were enormous agricultural companies that had changed their seeds, and there was an ecosystem built. Okay, so we are fully aware of all of that. But the truth is that we've been modifying organisms continuously. I mean, that is how you get a strawberry in the middle of the winter, So, one of the things we're going to have to contend with is, I'll give you an even crazier question. Once we're modifying things, do we need to say that something is, what does natural mean? If everything is still natural, we haven't introduced outside synthetic, truly totally made up chemicals, we've just tweaked a mushroom so that it doesn't brown as easily when you slice it, then how is that natural? It's still organic. It's been tweaked. So I think people like us and proponents of all of this technology, it's going to be rough for us to have a reasonable conversation about this because that marketing has worked so well. And there's a chapter in the book that deals explicitly with this and misinformation. It has to do with golden rice. We tell the story of a couple of scientists who had the best interests of humanity at heart, edited rice to make it more full of nutrients. It wasn't going to be a panacea, but it was going to be better than what existed. And most of the world's, requires rice. It's part of their daily diets, and it's stripped of all of its nutrition. They were going to give away the IP. They were going to give away the seeds. And through a series of, to be fair, a couple of bad decisions and some huge marketing campaigns, the whole thing imploded. It's a terrible, terrible story that really illustrates why we're going to have to redouble our efforts to help people understand that, edited things are not evil, horrible things. We just have to reframe the conversation. It's going to be rough, though.
I think it happens naturally over time, especially as the I'm not as we move to these next generation products and techniques. I think that there's some really compelling positives, and eventually the marketing campaigns will start to focus on those. GMO has been around for a long time, but it turns out it's only a very small and very vocal group that kind of drive that conversation. And most people, it's just like, no, it tastes great.
Yeah, but it's fear. I mean, one of the central
fear-based
things that drives it. There have been a couple of studies shown that, like, humans, we don't like it when we don't finish our sentences, right? So we fill in. A lot of people will catastrophize and fill in the end of those sentences, and it's the fear that drives oftentimes how we make that completion, how we think about the future. The reality is that Dolly the sheep in the 90s was unveiled. It was a cloned sheep. It seemed to come out of nowhere, but of course it didn't. It was the product of very long periods of research. But like, humanity lost its mind. Collectively, we freaked out on a planetary scale. The Pope had to make a special edict. President Clinton at the time had to have a special press conference. And the years subsequent to Dolly, we didn't wind up with a apocalyptic hellscape of demons spawned sheep. We wound up with therapeutics. And literally everybody's forgotten. How many times do I talk about Dolly the sheep and nobody has any idea what I'm talking about? So again, it's useful for us to think about, if we're coming to a snap decision about something, is it fear that's driving us, and where does that fear come from? Unfortunately, it's going to be hard to wind some of that back, especially coming out of this pandemic where misinformation really dictated so many of the thoughts and decisions that people had. But Andrew tends to see like happy, optimistic futures, and I'm the one that's constantly doom and gloom, which is why we're a good pair. We balance each other out.
All right, let's have the next question. I think we have time for one more question. So Sajiv would like to say, a future in which anyone has super user access to living systems seems incredibly volatile. How do we manage the trade-off between democratizing biohacking and reducing the risk of catastrophe?
I'm leaving that to you, Amy.
Thanks, Andrew. Okay. So yeah, you're right. There are potentially really big problems for us on the horizon. But here's what I will say. I think I can speak for both Andrew and myself in saying that we are not very worried about individual biohackers, at least not for the interim. Most of the people doing experiments, playing around with this stuff are in high security labs, or they're teachers. They're just working out the basic mechanisms and trying to understand how cells work and identifying genomes. So that's really not our concern. Our concern is, in a way, more structural. So what happens when IP clashes with science? We've already seen that. So that cell that got booted up in 2010, as Andrew mentioned. So when scientists create when they're doing some of this work, they digitally watermark it by embedding additional benign, meaningless code. And in this particular case, the code that got included was a quote from a portrait of the artist as a young man by Joyce. The quote is, "To live, to err, to fall, to triumph, to recreate life out of life." And there were some other bits and pieces of code that were there. Anyhow, turns out the Joyce estate is super litigious, and they were super upset that somebody had scraped and used a couple of lines from a Joyce poem inside of a living organism. And they were very upset, but where are you going to send a cease and desist letter? Like, what? How do you tell? We don't have any case law that says you're not allowed to put copyrighted content inside of a living organism. This seems like a little bit of a flip response, but it's actually a huge, like, I'm more concerned about that, because the reason that we wound up with a bunch of hired hands in the Philippines stomping down the golden rice demo patch where they were trying to finally grow and prove that this stuff worked. A bunch of people were hired to pretend like they were farmers and stomp it all down. The reason of this was because of fear and misinformation and IP. This is a huge problem in the United States. It's who covers what patents for what parts of biological code and who can have access to it. And we have no long-term vision. We have no long-term funding in this country, and many other countries don't either. But I will tell you who does, and that is China. China has a long-term roadmap for, as you know, artificial intelligence and for synthetic biology. It is part of their 14th year plan. Part of their sovereign wealth fund is going to fund some of this stuff. And this is no comment on the individual scientists or the individual researchers within China who are doing great work, and most times they're doing it for the public good. But the government has very different ideas. And the government is very opaque in its reporting and allowing others to see what's happening. So the kinds of stuff that we're concerned about are not individual biohackers gaining great access to life. It's these big structural challenges that we need to start working through, because at some point, we don't want to be in a situation where we've got a cyber biological war or some type of weird cyber biological malware that, like, nobody knows what to do with. That kind of stuff is scary, and we need to really have a smart dialogue about it now so that we can start preparing. And also, you can use this stuff to make beer and wine, so that's good too. It's, we got to be practical.
Awesome. So we are out of time. Amy, Andrew, thank you so much. Once again, the book is The Genesis Machine, and it should be available now. And that's all for today. Thank you.
Thank you.